So hopefully this will just be a quick recap of an intro to the very beginning of acids and bases. So just as a reminder, water is what we call amphoteric, which means it can act as an acid or a base. And the reason why it does that is because when water molecules are bumping into each other, we got to remember that the oxygens are very electronegative, and occasionally one water's oxygen will actually steal a hydrogen from the other one. So if we imagine that this water molecule has a hydrogen taken from it, it ends up turning into hydroxide. Okay, but it's really just the hydrogen's proton that's being lost, which is why that negative still lingers around. And then the other water molecule, having gained a proton, now turns into this molecule. And just as a reminder, okay, this one is called hydroxide, and this one is called hydronium, which was a new molecule when we first learned this. The first model for acids and bases was pretty simple. It just said that when acids dissolve in water, they directly increase the amount of hydrogen protons that are in the water. So this hydrogen that came from hydrochloric acid would then add itself to a water molecule and turn into hydronium. Okay, and if something was a base, then that means that it would directly increase the amount of hydroxide. So some of it would turn into sodium, but sodium by itself is neither acidic nor basic, and some of it would turn into hydroxide. So the very first model said that acids are things that increase the concentration of hydrogen, bases are things that increase the concentration of hydroxide. And that definition is still true, but the method that we explain it with has changed. The more updated approach is we actually look at acid and base dissolving almost as if it's a reaction with water. So it's really what is the substance turning water molecules into rather than just what is it dissociating into. So when the hydrogen gets lost from the hydrochloric acid, we see hydronium being created, and then the other product is chlorine. So this is a dissolving process that only increases the acidic content of water. Okay, if we look at ammonia reacting with water molecules, ammonia, remember from way back, is a molecule like this. Okay, the presence of that electron group up there makes the end very electronegative. And so it's going to be more likely to steal a hydrogen than to donate one. So that means that we end up with, that does not look like an N, we end up with an H4, where the nitrogen has attracted an extra proton and depleted the water by one proton. And now you have an increase of only the basic component of water. The other important thing to remember is now that we're looking at these like they're chemical reactions, we have to consider the fact that they could potentially go backwards, which means that they have to be acid-base reactions in either direction. So if we now consider acids to be proton donors, so always giving a hydrogen to water, and we think bases are proton acceptors, which means taking hydrogen from water, we can look at a full list like this and determine what thing is what. So since this substance is losing a hydrogen and giving it to water, that's going to be the acid, which means water is acting as the base. On the other side of the equation, if we read the reaction going backwards, our hydronium over here, okay, then that has to now become the proton donor. So that means that hydronium is what we call the conjugate acid, and the acetate, which is the C2H3O2, has now become what we call the conjugate base. So if this reaction ever goes backwards, okay, it will then be the proton acceptor instead of the proton donor. Now, this second reaction might be a little bit harder for you to get your head around at first because you're not used to looking at these organic compounds that are really large like this. Okay, always remember that what we're looking at is what is this going to do with water. If you have a substance here that has an extra positive charge, it wouldn't really make any sense that it would steal another positive charge. In fact, what ends up happening is the opposite. So remember that water can act as an acid or a base. It just reacts to whatever is dissolving in it. And if water is very polar, that oxygen, which is really electronegative, is going to be really attracted to a substance that has an extra proton lingering around. So in that case, this is going to get rid of that extra positive charge and give it to water. So that means that this is going to act as the acid, water is going to act as the base. So what I need to show on the other side is that C6H5NH2 has lost not just a hydrogen, but also that positive charge, because that's really what it was getting rid of. And that means that it was turning into hydronium. So if we were going to take this reaction and go fully backwards, hydronium would have to be the new proton donor, so it's a conjugate acid, and then this substance which is left behind, C6H5NH2, would have to therefore be the conjugate base. When we look at bases, we're kind of doing the same thing, but how are you going to be able to tell if it's a base? That's a great question. So you have to think about what is in the molecule. Is it going to be more likely to take a hydrogen from something, or is it going to be likely to give a hydrogen? So sometimes there's going to be clues in the questions. It'll say like this behaves as a base, or it'll give you a KB. But the clear indicator that these three things have something in common is they all have this nitrogen, which we associate that with really strong electronegativity. So these three substances tend to act as bases, which means we need to show water losing a hydrogen instead of gaining one. So if I add a positive charge, this one turns into NH4 plus, and water is now just OH. So this was a base, which means that water acted as the proton donor and it was the acid. That means if going backwards, this would be the conjugate acid and this would be the conjugate base. So if I just skip to the third one here, same thing. C6H5N does not change, but I want to show that it gained a proton, which is in the form of a hydrogen, and that what was left behind was a hydroxide. So this acted as the base, water acted as the acid, which means going backwards, this would be the conjugate acid, and this would be the conjugate base. Okay, so acid and base strength is something that's really misunderstood because people assume that it's talking about the pH of the solution, but it's not. It's talking about the dissociative power of the molecule. Does it all dissociate almost like it's an ionic compound, or does it only partially dissociate? So something that is strong is what we would call a full dissociator. So like hydrochloric acid is going to completely turn into hydrogen ions and chlorine. 100% of the entire substance is going to dissociate in water. So in terms of equilibrium, we learned what that means about K value. Notice that there's no backwards arrow here. The K value lies really far to the right because it essentially is not a reversible reaction. To recognize what is a strong acid involves a little bit of memorization. I know that you had to learn these three and this one by heart. Okay, HBr and HI are also strong acids. Strong bases are a little bit easier. Anything that has a hydroxide on it is directly considered a strong base. So if you see hydroxide on a molecule, you can consider that to be strong. And what strong means, again, just to emphasize, here's the difference. If you take all these molecules of an acid or a base and you put them in water, notice all of the ions separate. Okay, that's the strong electrolyte part of what we're talking about. It dissolves like an ionic compound instead of a covalent one, as opposed to a weak acid or a weak base, where only a small portion of the substance is going to dissociate. Notice that I say dissociate, not dissolve. The weak acid and weak base still dissolve 100% in water. They just don't dissociate at the same rate. So that means, like, because there's a lot of covalent molecules that dissociate in water. So as long as it's polar, it's going to dissolve in water. It just might not ionize at the same rate as a strong acid or a strong base. If we're comparing what we would consider to be weak substances, which means that they do not 100% dissociate, we need to use their K values in order to compare them to each other. So the larger the K value means the more forward the dissociation. So you're going to be making more and more and more ions as you dissolve those in the water. for example, I would say iodic acid on this chart has the largest Ka. So that means even though these are all considered weak acids, it is the strongest of these weak acids. Okay, a lot more of it dissociates in water than, say, acetic acid, which is only 1.8 times 10 to the negative fifth. Okay, or way down here, hydrogen peroxide, 1.8 times 10 to the negative 12th. So basically hydrogen peroxide is not any more acidic than water. The Ka value of acids also gives you an indicator of how strong or weak of a conjugate that substance would make. So for example, iodic acid is HiO3. The opposite of HiO3 is the conjugate base version of that substance, which would just be the iodate ion. If iodic acid is a really strong, weak acid, it means that its conjugate base is going to be really, really weak. So basically, iodic acid is way better at being an acid than iodate is better at being a base. Okay, same thing if we look at like cyanic acid. HOCN has a relatively large Ka, so 3.5 times 10 to the negative 4, pretty strong. That means that HOCN is going to be pretty good at donating an H. So that means that consequently OCN minus would be really bad at accepting the H back. So there's always like a preferred side. Does something prefer to be its acidic version, or does it prefer to be its basic version? So if you're looking at a question like this, where you have a bunch of conjugate bases, you have to think, what was the acid that they originally came from, and what were the Kas, and then compare them to each other. So I know that Cl used to be HCl, Cn minus used to be HCN, and OCN minus used to be HOCN. HCl is a super, super strong acid. So Ka, huge. Okay, it doesn't even have a value. If we try to look it up on this chart, it's not even on there. If we look at HCN, the K is 6.2 times 10 to the negative 10, 6.2 times 10 to the negative 10, and HOCN is 3.5 times 10 to the negative 4. 10 to the negative 4. Okay, so before we can say which one is the best base, we have to think which one is the best acid. Okay, this one is definitely number 1 acid, this one would be number 2, and this one would be number 3. Their base version is naturally the opposite of their acid version. So that means that going backwards, Cn is going to be the strongest acceptor of an H molecule. Of an H proton. So it's much more likely that it'll turn back into HCN. This one would then be ranked second, and that means that our Cl is going to be the weakest base. So basically chlorine, once it has detached from H, it never goes backwards. It's a terrible, terrible base.